Hello once again, this is my second video in my channel, Numeropedia, and this one's going to be about the Pascal's triangle. What is the Pascal's triangle, we must ask ourselves first? Well, a dictionary definition from Wikipedia would probably be, in mathematics, Pascal's triangle is a triangular array of the binomial coefficients. Basically, the Pascal's triangle is just a triangle made of numbers. The number 1 is on the point on the top. The top row is the 0th row. The first row is made up of two ones below the 0th row. So here I have a representation of a Pascal's triangle. Here are some more rows in the Pascal's triangle. So while these are appearing, let's see if we can find a pattern in here. And indeed, we find out that each row makes up a power of 11. Well, this pattern sort of stops on the 5th row. We'll see what happens. The problem with the numbers 1, 5, 10, 10, 5, 1. From before, we saw the fact that the first 5 rows in the Pascal's triangle form powers of 11 by their corresponding row number. For instance, the 0th row is equal to 11 to the 0th. We see that this pattern all of a sudden stops at the 5th row, as shown above. When you find what 11 to the 5th is, you get the answer 161,051. The above answer is clearly not 11 to the 5th. But is it? Let us look carefully at the 4th and 5th row. The 4th row, 1, 4, 6, 4, 1. The 5th row, 1, 5, 10, 10, 5, 1. Well, a solution we can come up with is, one obvious trait that we realize is that the 4th row is all of a sudden 1-digit numbers, and then the 5th row contains 10, which is a 2-digit number. Whoa. But if we write each digit down in expanded form, for the 4th row, we will get 10,000 plus 4,000 plus 600 plus 440 plus 1, which is 14,641. So if we write the 5th row in expanded form, we will get 100,000 plus 50,000 plus 10,000 plus 1,000 plus 50 plus 1, which is indeed 161,051, which is 11 to the 5th. This pattern continues on forever in the Pascal's triangle. And this is one of the many simple patterns that appear in the Pascal's triangle. Let us look at the same Pascal's triangle once again. This time we're looking for another pattern. If we look closely, we realize that each row is also a power of 2. Not the power of 2, not the powers of 11 that we saw before, but actually the sums of each row. For instance, the first row is a sum of 1, then the 0th row is a sum of 1, the first row is a sum of 2, and the sum of 4, sum of 8, and so on. And no, 11 is not 2 to the 1st. And as I said before, I mean the powers of 2 is the sum of each row. For instance, 1 is equal to 2 to the 0th, whilst 1 plus 1 is equal to 2, which is equal to 2 to the 1st. This pattern continues on forever, with no issues or minor confusion, so unlike the powers of 11. Blaise Pascal is, as the name suggests, discovered this triangle in the first place. He also realized that this is one of the many patterns in it. Well, of course, many people have noted this triangle before Pascal himself. One of these people is Giussian, I believe that's how you pronounce it, who noted this triangle in the 11th century. In fact, Fibonacci also noted this triangle, which contained the Fibonacci numbers within it. More on that later. Now, binomial coefficients. For those of you who are confused with this unknown term, it's basically another name for a combination. So, combination of n, r, well, in that image I got nk, but close enough. You get the formula n factorial over k factorial times all in parentheses n minus k factorial. Using the Pascal's triangle is extremely easy to find a binomial coefficient. Here's how. We get the Pascal's triangle, and each row corresponds with each term corresponds with the binomial coefficient. Don't forget to subscribe, like, and hit the bell icon if you enjoyed my video. And I will be posting more videos about this series later on. Thanks for watching.